Let's talk about reality. You probably think you have a pretty good handle on it. You throw a ball, and it flies in a predictable path. You leave your keys on the table, and they stay right where you left them. This is the world we see every day, governed by rules we can understand and trust. But I'm here to tell you that everything you think you know, those solid, dependable rules crumble when you look at the world on the tiniest, most fundamental scale imaginable. Down there, the realm of atoms and particles. The universe plays by a completely different, mind-bending set of rules. It's a place called the quantum realm. Imagine you have a wall with two thin, parallel slits in it. Now, stand back and start throwing baseballs at the wall. Some baseballs will bounce off, but some will go through one of the two slits and hit a backstop wall behind it. If you mark where each baseball lands, you'll end up with two distinct stripes on the backstop, one stripe lined up perfectly behind each slit. This is exactly what you would expect. It's simple, it's predictable, and it follows the rules of our everyday world. Baseballs are solid objects, and they go through one opening or the other. Easy peasy. Now let's change the game. Instead of baseballs, we're going to shoot tiny little particles, like electrons, one by one. An electron is a single, indivisible particle, just like a tiny baseball. So, you would expect to see the same result, right? Two stripes on the backstop wall, one behind each slit. But that's not what happens. Instead of two stripes, what appears on the backstop is a whole series of stripes, an interference pattern. This pattern is what you get when waves pass through two openings, like water waves. The waves interfere with each other, creating peaks and troughs, which results in multiple stripes. This result is bizarre. We are firing single electrons, one at a time. How can a single particle create a pattern that suggests it's interfering with itself? It's as if each electron, all by its lonesome, is somehow going through both slits at the same time, behaving like a wave. It splits, interferes with itself, and then recombines to hit the backstop. This experiment, known as the double-slit experiment, is the quintessential demonstration of quantum weirdness. It shows us that at the quantum level, particles don't just act like particles, they also act like waves. This is called wave-particle duality. But here's where it gets even stranger. The scientists, baffled by this, decided to place a tiny detector at the slits to see which slit each electron was actually going through. They wanted to catch the electron in the act. But the moment they did that, the moment they observed the electrons, the interference pattern vanished completely. The electrons suddenly stopped acting like waves and started acting like baseballs again, creating just two simple stripes on the backstop. The very act of watching changed the outcome. It's as if the universe knows when it's being observed and changes its behavior accordingly. The double-slit experiment gives us a perfect entry point into one of the most famous concepts in quantum mechanics: superposition. What does it mean? In simple terms, a quantum particle can exist in all of its possible states at the same time. Think of it like a spinning coin. While the coin is spinning in the air, before it lands, is it heads or tails? Heads? Tails? The only honest answer is that it's in a state of both heads and tails simultaneously. It's only when the coin lands, when its state is measured, that it settles into one definite outcome, either heads or tails. Superposition is the spinning coin phase for a quantum particle. Before we measured which slit the electron went through, it was in a superposition of states, going through the left slit and going through the right slit at the same time. This is why it could behave like a wave and interfere with itself. The electron wasn't a solid little ball traveling a single path. It was a cloud of probabilities, a wave of potential that covered all possible paths at once. This isn't a guess or a theory. It's the mathematical reality that allows us to make incredibly accurate predictions about the quantum world. A particle remains in this fuzzy state of all possibilities until it is forced to choose. This idea is completely alien to our everyday experience. A car can be in the garage or on the street, but not both. You are either reading this sentence or you are not. But for an electron, its position, its spin, or its energy level can be a mixture of different values all at once. It's not that we just don't know which state it's in. The particle itself genuinely does not have a single, definite state. It exists as a spectrum of possibilities. To illustrate just how strange this idea of superposition and measurement is, physicist Erwin Schrödinger came up with a famous thought experiment. It's a story, not a real experiment, designed to show the absurd consequences of applying quantum rules to our macroscopic world. Imagine you place a cat inside a sealed steel box. a tiny speck of a radioactive atom, a Geiger counter, a hammer, a vial of poison. If the radioactive atom decays, the Geiger counter will detect it, triggering the hammer to smash the vial, releasing the poison, and, well, you know. The radioactive atom is a quantum object. According to quantum mechanics, its state is governed by superposition. Over a certain period, say 1 hour, there's a 50% chance the atom has decayed and a 50% chance it has not. Until we measure it, the atom is in a superposition of both states, decayed and not decayed at the same time. Because the cat's fate is linked to the atom, the cat too must be in a superposition. Inside the sealed box, before we open it, the cat is simultaneously both alive and dead. Alive, dead. It's not one or the other. It's a blur of both possibilities. This is where our intuition screams, "That's impossible." A cat can't be both alive and dead. It has to be one or the other. And that's exactly Schrödinger's point. He created this morbid little tale to highlight the bizarre disconnect between the quantum world and the world we live in. How does a quantum superposition of an atom translate into the definite state of a large object like a cat? Where is the line? When does the fuzziness resolve into the solid certainty of our classical world? This is known as the measurement problem, one of the deepest mysteries in physics. The story of Schrödinger's cat captures the role of the observer. The cat remains in its absurd alive and dead state only while unobserved inside the box. The moment you open the box to check on the cat, you are performing a measurement. The act of looking forces the universe to make a choice. The superposition collapses, and the cat becomes either 100% alive or 100% dead. The observer doesn't just discover the cat's state. The observer's interaction creates the definite state. In the quantum world, there's no such thing as a passive observer. If you thought things couldn't get any weirder, hold on to your lab coat. Let's talk about quantum entanglement. Albert Einstein famously called it spooky action at a distance because it seemed to defy the speed limit of the universe, the speed of light. Entanglement happens when two or more quantum particles become linked. Their fates are intertwined no matter how far apart they are. They essentially become a single system. One particle on Earth, the other on the other side of the galaxy. They are like a pair of quantum twins. Imagine you have two special coins that are entangled. If you flip them, they are guaranteed to land on opposite faces. If one is heads, the other is absolutely, positively tails. If one is tails, the other is guaranteed to be heads. Now, you give one of these entangled coins to a friend, and keep the other. Your friend travels to the moon. You both agree to look at your coins at the exact same time. The moment you look at your coin and see that it's heads, you instantly know, with 100% certainty, that your friend's coin on the moon is showing tails. The spooky part is how this information seems to travel. Before you looked, your coin was in a superposition of heads and tails. So was your friend's. But the moment your measurement collapsed your coin into heads, your friend's coin, hundreds of thousands of miles away, instantly collapsed into tails. The information about your coin state seemed to travel to the other coin instantaneously, faster than light could ever travel. This apparent violation of the cosmic speed limit is what bothered Einstein so much, but experiment after experiment has proven that this is exactly how the universe works. This isn't just a theoretical curiosity, it's a real, measurable phenomenon. Scientists have entangled photons, particles of light, and sent them miles apart through fiber optic cables. Every single time, measuring the state of one photon instantly influences the state of the other. It doesn't mean we can send messages faster than light. That's a common misconception. But it does reveal a deep, mysterious connection woven into the very fabric of reality. It suggests that our concept of space and separation might not be as straightforward as we think. The universe, it seems, is far more interconnected than we ever imagined. You might be thinking, this is all very fascinating, Bill, but what does it have to do with me? This is stuff for physicists in labs. But the truth is, you are using technology based on quantum mechanics right now. The quantum world may seem distant and strange, but it's the foundation of modern tech. Without understanding how electrons behave in silicon, we wouldn't have the transistor, computers, smartphones, the internet. Consider the laser. A laser works because electrons are stimulated to release photons that are all perfectly in sync. Barcode scanners at the grocery store, Blu-ray players, delicate eye surgery. The GPS in your phone or car relies on the incredible precision of atomic clocks. Atomic clocks use predictable quantum jumps of electrons between energy levels to keep time so accurately they'd only lose 1 second in millions of years. Quantum mechanics isn't just a theory, it's a practical tool. And this is just the beginning. Superposition. Entanglement. Quantum computers promise to solve problems impossible for classical supercomputers. New medicines, new materials, breakthroughs in artificial intelligence. Quantum cryptography could create unhackable communication networks. Any attempt to eavesdrop on an entangled signal would, by observing it, change it and alert the users. The future is quantum. Next time you pick up your phone or turn on your computer, take a moment to consider the invisible, bizarre world that makes it all possible. That solid, reliable device in your hand is powered by the fuzzy, probabilistic, and downright spooky rules of quantum mechanics. It's a powerful reminder that the universe is layered with mysteries, and by exploring its most fundamental rules, we can unlock technologies that change the world. The quantum realm isn't a far-off fantasy. It's the engine of our modern age. What quantum idea surprised you the most? If you found this mind-blowing, subscribe and hit the bell. What quantum concept baffles you most?